Good afternoon, my dear students. Today our topic is numerical methods. Mainly the chapter will be solution of algebraic or transcendental equations. So with the advent of the modern high-speed electronic digital computers, the numerical methods have been successfully applied to study problems in mathematics, engineering, computer science, physical sciences such as biophysics, physics, atmospheric sciences, etc. The art and science of preparing and solving scientific and engineering problems have undergone considerable changes. So, this is due to the following two reasons. Number one, the mathematical problem is to be reduced to a form which is suitable to machine solution. And number two, several million operations are performed per minute on a high-speed supercomputers. And it is difficult to check the error at any stage. So, we are talking about the solutions of equations. Finding one or more roots of an equation, fx equal to 0, is one of the more commonly occurring problems of applied mathematics. So, in most cases, explicit solutions are not available. And we must be satisfied with being able to find a root to any specified degree of accuracy. The numerical methods for finding the roots are called iterative methods, and they are the main object, or maybe you call subject of this chapter. So, the problem of great importance in science and engineering is that determining the roots or zeros of the equation of the form fx equal to 0. Fx can be a polynomial equation. You know that the polynomial equation has the form a0 x to the power n plus a1 x to the power n minus 1, a2 x to the power n minus 2, etc. This is the algebraic equation. An equation which contains polynomial, exponential functions, logarithmic functions, trigonometric functions, etc. These are called transcendental equations. So what about roots? A number alpha for which f alpha is 0 is called a root of the equation fx equal to 0, or a 0 of fx. Geometrically, a root of an equation fx equal to 0 is the value of x at which the graph of the equation y equal to fx intersects the x-axis. That is geometrically. And what about simple root? A number alpha is a simple root of fx equal to 0 if f alpha equal to 0 and f prime alpha not equal to 0. Then we can write fx equal to 0, fx as x minus alpha gx, provided that g alpha not equal to 0. This is from the factor theorem. And what about multiple root? A number alpha is a multiple root of multiplicity m if fx equal to 0 and if f alpha equal to 0, f prime alpha equal to 0, etc. If power m minus, it should be f power m minus alpha 0, that is m minus 1th derivative should be 0, but mth derivative not equal to 0, then we can say fx equal to fx as, we can write fx as x minus alpha whole to the power m gx, provided that g alpha not equal to 0. That is the concept of multiple root. If m is a multiple root of order m, then m minus 1th derivative is not equal to 0, but mth derivative is not 0. That is the concept of multiple root. Now, some prerequisites before we start the main numerical methods. So next is initial value theorem. If fx is continuous in the closed interval ab and fa and fb are of opposite signs, then there is a real root alpha of the equation fx is equal to 0 such that a less than alpha less than b. So if this is the curve, suppose this is the axis and suppose this is the curve, so this is a and this point is b and this is the fx curve, and look at that fx is continuous in the closed interval ab, and if a is negative fb is positive, so fa and fb are of opposite signs, then there is at least one point alpha where the curve cuts the x-axis. So alpha is a root of the real root of the equation. If further fx is differentiable in the open interval ab and monotonic, if it is also monotonic, that is if I either f dash takes positive or f dash takes less than 0 in ab, then fx is strictly monotonic and the root alpha is unique. So that is your initial value theorem. Now, location of roots. All the methods of numerical solution of equation consist of two stages. We have two stages in numerical methods of finding the solution. The first stage called location of the roots, at which rough values of the roots are obtained, and the second stage which consists in improvement of the rough value of each root to any desired degree of accuracy. So there are actually two stages. First stage is location of the roots. Next is the second stage is if you once you got the location or interval, next stage is to improve the rough value of each root to any desired degree of accuracy. That is the two stages of the methods. Now, in location of the roots, a method of improvement of the value of the root at the second stage usually involves a process of successive approximations or iteration in which a sequence xn is generated by the method in question. So, in any method, you have to find out the sequence of iterations, starting with the initial rough value x naught of the root alpha obtained in the first stage. So, in the first rough value x naught is obtained, then you have a sequence of iteration xn. Now, such that xn tends to alpha as n tends to infinity. So, root alpha is obtained in the first stage such that xn tends to alpha as n goes to infinity. So there is a successive iterations actually. Thus, xn is called the nth approximation or iterate, gives a sufficiently accurate value of the root alpha if n is large enough. Okay, so there is a sequential concept. Now, error. What is your error? The error epsilon n at the nth iteration is defined by epsilon a is equal to alpha minus xn, and we define hn by hn equal to xn plus 1 minus xn. The iteration converges if and only if epsilon tends to 0 as n tends to infinity. So whenever the iteration converges, the necessary and sufficient condition for the convergence of iteration is that the error nth term of the error tends to 0 as n goes to infinity. So, and the error is given by, error can be calculated by alpha minus xn. That is, you already know that error is calculated by the true value minus the approximate value. Okay. And the condition of convergence. What is the condition of convergence? Given a method of iteration, our primary task is to find the condition under which the iteration converges. That is called the condition of convergence. So in every method, there is a special type of condition of convergence, which is very important to study. So condition of convergence, we have to study this condition of convergence of that method. Now, what is the error equation? We may try to express epsilon n plus 1 in terms of epsilon n and epsilon n minus 1, etc., which is called the error equation. It may relate the nth term of the error and with the previous error, with the next error. So this type of equation is called the error equation. And what is the estimation of the error? Upper bound. We try to find an upper bound of modulus epsilon n in terms of hn. This is called the estimate of the error. Already hn is calculated here. Look at the previous step. Hn can be calculated by step length, that is xn plus 1 minus xn. So that is the estimation of the error. Now, what is the order of convergence? That is very important definition, and you need to calculate somewhere the order of convergence of the method. In every method, there is an order of convergence. If an iterative method convergence and two constants p greater equal to 1 and c greater than 0 exist, such that limit n goes to infinity, modulus of epsilon n plus 1 by epsilon n plus 1 whole to the power p equal to c. So this is the relation, and p is called the order of convergence of the method, and c called the asymptotic error constant. So order of convergence of the method is very important. More the order of convergence of an iterative method, the method will more converge, rapidly converge. So an iterative method with higher order of convergence than 1 is expected to be rapidly convergent. So we'll discuss later on. There are some methods whose order of convergence is more than 1. So that method is very rapidly convergent, very fast. Convergence is very fast. So that is the, actually this, in this way you have to convert, and it is defined by this limiting expression. Limit n goes to infinity epsilon n plus 1 by epsilon n plus 1 whole to the power p equal to c. P is called the order of convergence and c is the asymptotic error constant. Now we'll talk about different methods. So first of all, there is a method called method of tabulation. It is a very simple method. Number 2, method of bisection. Number 3, Newton-Raphson method. Number 4, method of regular falsy or regular false position. Fixed point iteration method. Also there is a graphical method and several methods, but in your syllabus we have to talk about these 5 methods. So first of all, let me talk about method of tabulation. This is a method of finding a rough location of the roots, first of all, in which the first select an interval which is expected to contain all the roots of the equation fx equal to 0. The value of fx are then tabulated in this interval with a moderate value of the step length, say h. Okay. So by noting the changes of sign in the table, we often differ in intervals of length h containing the roots. The function is again tabulated in each of the above intervals containing a root by using a smaller value of the step length, say h by 10, and look for a change of sign which gives an interval of length h by 10 containing the root. By repeating the method of tabulation several times, we get the required approximation to the roots. So this is the method of tabulation. Let me explain with a beautiful example. The example is not here in the presentation, but I will write the presentation, write in the presentation. Okay. So I will, let's, for example, the equation is, for example, the equation can be taken as 10 to the power x plus x minus 4 equal to 0. This is the equation. So let fx equal to 10 to the power x, this is a transcendental equation, plus x minus 4. Okay. So now you, by trial and error, you just assume that what is the value of f0? f0 will be minus 3, right? And which is less than 0. Let's calculate the value at f1. So f1, the value will be 7. So it is positive. Hence, there is a real root between 0 and 1, right? Now let us tabulate fx between 0 and 1 with step length 0.1, suppose 0.1. Let us tabulate the values of fx between 0 and 1 with step length 0.1. So what will be the table for you? So table 1, let us tabulate x and fx. So starting value of x will be 0, 0.0, right? Then your step length is 0.1. So 0.1, 0.2, 0.3, etc. And finally you have 1.0. Next, calculate the value of fx at these points. This is positive. Only need this is negative. This is also negative. Suppose this is negative, and suppose between 4 and 5 you have a changes. So suppose this is your negative, this is your positive. So there is a root between zero point 0.4 and 0.5, minus, and there is a change of sign, right? So there is a root between 0.4 and minus 0.5. So you look at that. First step was your rough approximation, rough location of the roots. First of all, you have a rough location of the roots. Location of the roots is 0 to 1. You have a real root between 0 and 1. Then you are improving the roots by the tabulation methods. So you are improving the root by the tabulation method, that is 0.1 step length. So you have a 1 decimal place for the roots, 0.4 and 0.5. You can again tabulate the root between 0.4 and 0.5 by step length 0.01. So your first value will be 0.40, next will be 0.41, next will be 0.42, etc. and lastly you have 0.50. So again, this is called improvement of the roots, and so on. You will get another interval, 2 decimal place, and again you can choose a step length 0.001. That will increase the value of the root by 3 decimal place. So in this way you can improve your roots. Okay, this is the method of tabulation. Okay, everybody. So this is the very beautiful method of tabulation. So that was explained here. You can go through these explanations also once again, and this is the example. Next is method of bisection. Next method. So in this lecture I will stick to my next lecture, that is method of bisection. We assume that the function fx of the equation fx is equal to 0 is continuously differentiable a sufficient number of times. Also, we assume that all the roots of the equation fx is equal to 0 are simple. First, we find by the method of tabulation a sufficiently small interval a0 b0 containing the only root alpha of the equation fx equal to 0 such that fa0 into fb0 less than 0. Okay, just like we have explained here, that you have to find out a small interval a0 b0 where the root lies. Okay, so you have a root, you have a point a0 and b0. In this interval you have a root alpha, right? Okay, this is the root alpha, and if a0 dot f b0 are of opposite signs. Okay, now we then proceed to generate the sequence xn of iterates as follows. We set x0 equal to a0 or b0 and x1 equal to a0 plus b0 by 2. So let me draw once again. So suppose this is your x0 and suppose your x0 is a0 and this is your b0. Okay, and calculate the midpoint of a0 and b0, that is a0 plus b0 by 2, and denote this by x1 equal to a0 plus b0 by 2. Clear, everybody? This is the diagram also. I am drawing the diagram also for your better understanding. So a0 and b0, suppose a0 if a0 and f b0 are of opposite sign, suppose a0 is negative, at a0 the functional value is negative and b0 the functional value is positive. So there is a roots between a0 and b0. Now suppose at x1, compute the functional value at x1. So if the value at x1 is positive, then the root lies between a0 and x1, x0 and x1. Okay? The root lies between a0 and a0 plus b0 by 2. Here is the root. Look at that. Here is the root, alpha. But because if there is a change of the sign, so that will give you the value of the root. If the sign at functional value at x1 gives you negative sign, then the root lies between x1 and b0. This is the root. Again, you have to find out the midpoint of x0 and x1 and do the same process. Repeat the above step. So this is how the interval reduced. So if a0 x0 less than 0, we write a1 equal to a0, b1 equal to x1. And if x1, if b0 less than 0, we write a1 equal to x1 and b1 equal to b0. So that in either case, a1 b1 contains the root alpha and b1 minus a1 equal to b0 minus a0 by 2. We set again x2 equal to a1 plus b1 by 2 and repeat the above step and so on. This is the process of bisection method or interval halving method. This is also called. So let me again explain with a diagram. Okay. So let me give you again a diagrammatic representation will give you a very clear picture. So yeah, this is the space you have. So suppose this is the thing. Now this is your a0 initially. This is your b0. a0 b0 contains the root because if a0 f b0 times f b0 less than 0. Okay. Now this is your x1. Suppose x1 is a0 plus b0 by 2. Okay. This is the midpoint. Bisect. You are bisecting the interval a0 b0. Now at a0, suppose the functional value gives you the negative sign. And this is positive. So there is a root between a0 and b0. And at x1, suppose if a0 and if x1 less than 0, then this interval contains the root. So that means this is positive. Okay. So negative positive gives you the interval contains the root. So if a0, if x0 less than 0, then this is called, this is actually a1 and this is actually b1, suppose. Okay. Again, so this interval a1 b1 contains the root. Okay. Otherwise, if x1 if b0 less than 0, then this is your a1, then this interval contains the root. Okay. Otherwise, if this is negative, then this interval contains the root. The interval b1 and b0 contains the root. Again, suppose this interval contains a root. Again, you have to take a2 equal to a1 plus b1 by 2 and do the same process. Repeat the process. So look at that. Your interval gets decreased. So this way you have to compute the interval and go on. So this is a iteration process. Sequence of iterations you will get. And finally, in general, Having obtained the interval a n bn containing alpha, and if a n bn less than 0 and xn is equal to an or bn, we set xn plus 1 is equal to an plus b1 by 2 and an plus 1 equal to an, bn plus 1 equal to xn plus 1 if xn plus 1 less than 0. An or an plus 1 equal to xn plus 1, this is the generalization. Bn plus 1 equal to bn if xn plus 1 if bn equal to less than 0. So that an plus 1 bn plus 1 contains alpha and bn plus 1 minus an plus 1 equal to bn minus an by 2. Okay? So, again, you have bn plus 1 minus an plus 1 equal to bn minus an by 2, and that is equal to bn minus 1 minus an minus 1 by 2 squared, and so on. You continue this process substituting, you will get bn an equal to b naught minus a naught by 2 to the power n. Clear, everyone? So let epsilon be the error at the nth approximation xn. Then epsilon is equal to alpha minus xn. Therefore, epsilon n is modulus of alpha minus xn less than equal to bn minus an. That is, epsilon n is less than equal to modulus of epsilon n. This gives you the estimation of the error b naught minus an by 2 to the power n. So if n tends to infinity, this error goes to 0. Okay? Because you have 1 by 2 to the power n, this error goes to 0. So that is limit n tends to infinity, xn equal to alpha. Hence the iteration invariably converges. Hence the iteration invariably converges. So this is the beautiful method, and this is how you can calculate the error, estimation of error also. Okay? So this is the bisection method. This is a very important method. It is a very long process. You have to do a lot of number of steps, more number of steps required, but this method surely converges. So let's have some important notes, important points in this method. This method is very slow, number one, but it is very simple and will converge surely to the exact root. Why? That will explain later. So the method is applicable for any function only if the function is continuous within the interval where the root lies. This number 2, note 2, this method is also called the bracketing method, since the method successively reduces the two endpoints of the interval containing the real root. So actually the basic principle of the bisection method is NIP, nested interval property. And you know that nested interval property is very, very important in real analysis. So it is the nested interval property actually. In plus 1 is contained in in for all n belongs to the natural number. So NIP, basic principle of bisection method is NIP. So note 3 is very, very important. That is why the method is convergent. It contains exactly one root. And that is the famous theorem of Cantor's nested intervals. Nested sequence of closed and bounded intervals determines a unique real number, and that unique real number is a unique real root. That is why the method is surely convergent. So there is a question, which method surely convergence? Bisection method is surely convergent. And we are applying actually Bolzano's theorem on continuity with repeated application of Bolzano's theorem on continuity. Plus minus changes of sign gives you the that is the interpreted value property actually. So bisection method is actually surely convergent because of the NIP property, nested interval property, and Cantor's theorem. So this is the numerical methods of bisection. Next, I will give you lecture on Newton-Raphson method in my next lecture. Follow my lectures. Thank you, all of you.